All right, so we're still working through homework 15. This problem 233 on 57 is a sister to problem 61. And we're finding real roots of polynomials, and in this case, in a fourth order polynomial. So I'll try to treat every step here as we go along. The first step is how many roots are we possibly looking for? And the answer is fourth degree polynomial has as many as, or might have as many as 4 real roots. Doesn't mean 4, it has as many as 4, or at most 4 real roots. All right, let's quickly treat this this polynomial with Descartes' rule. I'm just going to count the sign change. I've got 1, 2, 3 sign changes for f of x. That means 3 or 1 positive real roots. That's what we're looking for. And if I kind of skip down here and put minus x into f of x, that polynomial looks like this. Which is that sign, minus 8. So there's just one sign change there, and therefore there's one negative real root that we're looking for. So that's useful. That says we are looking for a real root now. And by the way, it will be a negative number. So we'll keep that in mind as we go forward. And the next step then is to write down all the possible rational roots by using the rational root theorem. And it says, of course, that if there is a rational root, then it's a number p over q, where p is one of the factors of this last constant term, and q is one of the factors of the coefficient of the leading term. You get to catch a real break here because that coefficient is 1, the only factor is 1, and therefore you can kind of quickly say that p over q, the candidate rational roots, are plus or minus 1, 2, 4, or 8. So that brings that we've only got 1, 2, 3, 4 times 2. We've only got 8 candidates to try. And let's see if we can get lucky. If we put in 1 as a guess, we guess x equals 1. We get 1 minus 1 is 0. We get 2 minus 4 is minus 2 minus 8. Sorry, 1 didn't work, but you know I'm going to kind of do the following. I'm going to try minus 1 because things look close here. So I get 1 minus a minus 1, so I get 2 plus 2. There's a 4. There's another 4, so I'm up to 8, and I subtract 8. So sure enough, x equals minus 1 is a root. Let's fire up some confetti, have a party. Okay, because if x minus 1 is a root, so then x minus 1, aka x plus 1, is a factor. And I can use that factor. I'm not sure that's going to make it on the screen. And x minus 1 is a factor. And so I can use that to reduce this third order polynomial to this fourth order polynomial to a third order polynomial. That is, I'm going to come over here and do a little synthetic division. 1 minus 1, 2 minus 4, 8. Drop down the line, drop down that 1, multiply by minus 1, add these up, minus 2, multiply those, 4, multiply that, minus 4, add them up, minus 8. What did I just do? Minus 8, put the minus 8 there, 0. Sure enough, we knew that was going to happen. What this is telling ourselves, what this is telling us is that f of x can be written as x plus 1, that's the factor associated with this minus 1, times this third order polynomial, x cubed minus 2x squared plus 4x minus 8. All right. Well, we've made progress. We haven't found all the roots. What we have to do to find all the roots is find the roots of this third order polynomial. And I'll sort of shortcut it here. I'll just say we're looking for as many as 3 real roots. I'm not going to run through Descartes' rule. I will remind you, though, that we are looking for 1 negative real root. It looks like we've done it. And so we're still looking for 3 or 1 positive real roots. And so when we get to the rational root theorem, we're just going to look at the positive numbers. And that rational root theorem again tells you that you're looking for a set of numbers p over q of the set 1, 2, 4, 8, and just the positive versions of that. So I'll say p over q in this case is the positive, not plus or minus 1, 2, 4, 8. So we just have 4 candidates to check. 1 looks like it fails us. Here's 1 minus 2 plus 4 is 4 minus 8. 1 didn't make it. Let's see if we get lucky with 2. 2 is 8 minus 8, and 8 minus 8. X equals positive 2 is a root. Party on. Okay, and that means so x minus 2 is a factor. That takes us right back to synthetic division, trying to get x minus 2 out of this. Well, and let's go ahead and do that. So I'm going to put 2 here. I'm going to go 1 minus 2, 4 minus 8. This is going to work because x minus 2 is a factor. 0, 0, 4, 8. And sure enough, that says that we can write f of x as x plus 1 associated with the root x minus 1, x minus 2 associated with the root x equals 2, and then x squared plus 4. So we can find the roots there, but they're not real, and we're looking for just the real roots of the polynomial. Right, this says x plus 2, x squared plus 4 equals 0. That is resolved if x squared is equal to minus 2, and that's resolved when x is equal to plus or minus 2i times 2. Plus or minus 2 times I. Can I please get that smudge off of here? X is equal to plus or minus 2i. So if we were looking for complex roots, we would be looking for 4 roots, and there they are. X is equal to minus 1, x is equal to 2, and x is equal to plus or minus 2i. But the problem asks for the real roots. There's the answer. X is equal to minus 1, x is equal to 2.